Hi, my name is Thomas Bordeaux, and in this lab, we'll be analyzing and modeling the observed stationary motion of a spring in order to gain a better understanding of motion involving springs and the physics behind it. In order to understand the motion in the given video, we'll need to look at Newton's second law, the position update formula, the velocity update formula, as well as the work energy principle, consisting of kinetic energy, spring potential energy, and gravitational potential energy. We'll also need to be able to calculate the spring constant and the spring length. All these things can be done using the given equations on these slides. Upon importing the video into Tracker, we can see that the bottom of the spring stays constant even as the top falls until the top of the spring reaches the bottom. This data can further be seen in the Y position graph on the right-hand side of this video. Now, in Tracker, we've measured the motion of the bottom of the spring, and we can compare that using a known measurement, in this case, the height of Veritasium at 1.75 meters, as given in a tweet by him. Through further analysis of this video, we can determine that the time of the spring falling was 0.52 seconds. And using the equations on the previous slide, we can determine that the spring constant is 0.852 Newton meters, and that the original equilibrium length of the spring is 0.15 meters, or 15 centimeters. In this graph, we can see our measured Y position from the video, staying consistent at negative 1.3 meters below the top original position of the spring, until the spring top reaches the bottom of the spring at about 0.32 seconds. Now in GlowScript, we can begin to simulate this motion. We determine that the mass of the average spring is about 0.2 kilograms. You can see we've set that at the top. And we initialize our existing conditions. That the bottom of the spring is at negative 1.3 meters. That the top is at the origin. And also, we can establish our constants, the gravitational force, the spring constant, and a relaxed length of the spring. Now using this while loop, we can calculate the forces of gravity acting on the spring, as well as the force of the spring on itself. We can also using these forces, we can calculate the net force on each end of the spring, with the bottom of the spring being pulled down by the force of gravity, but up by the contraction of the spring, and the top being pulled down by the force of gravity. We calculate the momentum of the spring, and then using that, we can apply the momentum update formula to the velocity of the ball, and use that to apply to the position update formula. We can also update the spring length and its forces using the same while loop. Our result is this simulation, where the bottom of the spring, seen here in blue, stays in a singular position until the red part, the top of the spring, reaches it. Now, our simulated Y position can be seen here. And in this graph, we can contrast the actual versus the simulated. Now, in this graph, you can see that the simulated position is going at a much higher velocity, which means it's decreasing in Y position much faster than the actual measured experiment. We realize that this is due to not taking the center of mass of the object. So when we reach 0.32 seconds, we convert from tracking the singular point to tracking the center of mass, because unlike the actual experiment in our simulation, the spring does not stay together when it's contracted because it can clip through each other. In the actual experiment, the spring collides and becomes a singular point mass. And that's why when we switch to a center of mass at 0.32 seconds here, the data becomes much more accurate to the actual observed experiment. Thank you, and goodbye.